So one of the many reasons why you use C++ is performance. Not the only one, but one of them. And there are multiple competing solutions for taking advantage of hardware, especially in terms of parallelism. Even there are multiple competing solutions that would allow you to get that in heterogeneous platforms. When you try also that this is a standard C++, the number of solutions start to be narrower. So we are going to see one of those solutions, which is SYCL. And we have here Abhilash Majumder. I am very grateful for him to come in because, you know, somebody came from Switzerland, from Austria, from UK, but Abhilash made a long trip coming from India here just to give this talk. So thank you very much.
Thank you. Thank you.
And go ahead.
Yes. Thank you. Hello, everyone. I think it's a pretty great introduction. Thanks, Daniel. So before we start, I want to just know how many of you have heard of this term SYCL. Excellent. I mean, my talk will be reduced in like 20 minutes or so. Okay. So today's talk is going to be a very diverse topic, right? We are going to look into a lot of computing architectures, transformers, ChatGPT, Llama, and everything. Okay. And I hope you know or have heard of these things, in the contemporary industry. And there has been a lot of speculation to use the Python runtime because of overhead of using usability as well as the runtime performance, latency, and whatnot. So to cater to those needs, different organizations, hardware organizations, have released different kind of abstractions. So you have CUDA from Nvidia, right? I hope you have heard about CUDA. It's quite famous, and or if you have heard about hip from AMD. ROCM. So SYCL is somewhat similar, right? It all falls in the generic LLVM tree, I would like to say, but there are certain differences, and which makes it typically unique in this case. So when we are considering large exascale computing, we will come into that later. But just a question: do you know what this is? Any one of you? Excellent. Llama 3, excellent, thank you. This is the recently released model from Facebook, Meta, which is Llama 3, okay? It breaks all benchmarks available in LLMs currently for, prompting, automatic code generations, anything. So we'll be coming to this later, just to give you a hype. So this is what the entire ecosystem is, right? We want ChatGPT and we want to run it in a faster manner. We want to design our kernels. We want to have our own generic algorithms. Where do we write it? Using C++. So this is the entire ecosystem, particularly from Intel's perspective. This also caters to Nvidia and other AMD platforms as well. We will come into that later. So the contents that we are going to cover today is briefly about this. So we'll be covering, LLVM, the compiler backend, and how ICX and the ICPX compilers, which is typically the compilers which SYCL uses, to generate your SYCL code and compile your SYCL code. We'll be having a brief introduction to SYCL, semantics, how to write the code, some custom kernels. Now, this is where it gets interesting. We want the user to be free of any, let's say, design patterns, right? Who does not know C++ to that depth, but knows Python to a pretty good level, or any deep learning framework to a pretty good level. Let's say PyTorch or TensorFlow, if you've heard of it. So how are we going to link those kernels in SYCL with PyTorch to run these kind of big models, let's say ChatGPT or anything like that? Then we'll be talking about DPCT, the DPC++ toolkit, which is autocode transcompilation, migration from CUDA runtime to SYCL runtime. And I will be ending with references and conclusions, and hopefully a demo if time permits. But a prominent person said that talk is cheap, show me the code. So the code is available over here. All the resources, all the codes which I will be talking about is available on GitHub, open source. So yeah, moving ahead. So I think mostly everyone knows what LLVM is over here. So it's just kind of an industry standard toolkit which provides a lot of things. You can disassemble code, you can analyze bytecodes, you can migrate from one bytecode to another, from different hardwares, from let's say SPV to PTX or AMD GCNs. You can do lots of things. So the extension of SYCL actually came from this LLVM optimizer itself, particularly from the Clang. And it provides all kind of code generation, IR generation, representation, pattern transformation. And we are going to see some of the features, how we are going to link them and also compile our SYCL codes. This is the generic life cycle, or I would say the propagation pattern when it comes to any kind of C++ code, which is device specific. So let's say CUDA code or hip code or SYCL code. You are going to have a Clang extensions. So I apologize if I mispronounce Clang as Clang and vice versa. So C++, Fortran, Ruby, all these are typically the what you will be writing at the upper level. It will be converted to bytecode in BC format. And from that, you can do anything with it. Once you have the bytecode, you have everything that you want to do with it. You can disassemble the code. You can tweak certain intrinsics of the LLVM code for your typical architectures, let's say x86 or other architectures, and you can generate the output as well. This is what the Intel's compiler, LLVM compiler, is an addition on top of the standard LLVM compiler. So we have the DPC++ toolkit, the DPC++ compiler as well, and the Fortran compiler. So ICX is for your generally for the Windows builds, and the ICPX is the one that we'll be looking at today because it's Linux and everyone loves Linux. So C++20, the standard version that we are using for SYCL is C++17, but we are upgrading it to C++20, and these are the features that we are currently supporting: OpenMP offloading, vectorization, and lots of other things. So typically the architecture pattern inside Intel is somewhat like this. And this is the map of the entire how the code is actually coming down from the source, that is the source file, your CPP file, right, having SYCL kernels or SYCL code actually, to the end result, which is a fat file, a fat binary file. So you have your LLVM IR representations, you link them, right, and depending upon your hardware. So in this case, it is LLVM SPIRV, and then you have your targets, your specific hardware, hardware-specific optimizations at the compiler level. So generically, in the case of compiler optimizations, in the case of SYCL, the default is O2. If you know what O2 is, it's generally the standard auto compilation optimization which is there. But there are other factors to tweak it. So the target specific, I would say over here, the target specific LLVM compiler caters to those needs depending upon what you have specified, what kind of optimization you want to specify. And finally, we have the offload wrapper, and then ultimately the final linker. This linker is extremely efficient in the case that it is fast for linking different kind of source files which are having SYCL kernels along with source files which do not have the SYCL kernels. So you can link them, and there are many standards of this. You have gold linkers and all these kinds of things. But this is where the linking happens, and then you have the fat binary file. Once you have that, you can do typically anything with that output file, right? You can generate your output. You can link the processed or the compiled binaries to your Python runtime, which I'll be talking about, as your subkernels when it gets called from the Python side. So let's say, just a tidbit, if any one of you have used Hugging Face anytime soon for loading models from pre-trained or something like that, maybe in deep learning, when it goes and calls this kind of Python code, right, it goes inside these kind of binary files which are fat. They are not fat in general. The fat is a misnomer. Don't think like that. These are just compiled .so files, okay? And yeah. So some commands. I want to specify these commands before I go into certain code samples later on. But these are certain commands which are used for compilation. So in the case of compiling SYCL code, the ICX and the ICPX compiler is what is getting used. So generally the pattern is you are going to have -fsycl flag, which specifies that you're targeting for the SYCL runtime. And there are other arguments, I will come to that later, but it's typically is like ICPX -fsycl, your source file, and the output there you want to be. That's pretty simple. Okay, if you want to just have a single SYCL source file, you just want to compile and get the output. That's the way it is. For SPV, SPIRV Gen 64 builds, you can specify, what kind of device you want to have. So let's say fsycl target. For example, you have fsycl target over here, which is Nvidia. So if you replace that with a SPIRV 64, it will become for the SPV targets. So this is actually the crux of the thing of this entire talk. So that means the code that you write can be transcompiled to different kind of hardwares. So the same kernel can be made to run on PTX 64, assuming streaming multiprocessors are there, SM80 or SM90, and then it can auto-migrate to different, even in the case of HIP as well, AMD as well. So you do not have to write your kernels again and again. So once you've written a SYCL kernel, deploy that SYCL kernel across different hardwares. The IR will get generated automatically, and then link them back to your Python code and whatever you want to do with it. Yeah, that's pretty much what is over here. Yeah, so some other fancy variations of this SYCL command. Just want to give you a heads up. I mean, if you want to have this, just like I said, the standard runtime, if you want to include C++ 17, right? It is enabled by default, but you can try to. And for disassembling code, we all know that you can use the LLVM tool stack, right? You can use LLVM stack for any kind of code which is .bc. Right? You can disintegrate your code, disassemble your code to get to know all the different features and everything. Another way to do it there is another way. So here you see that I have written clang++ over here. Now, when you write clang++, when you write clang++, you have to specify that you are using DPCPP 17, right, with the fsycl flag. That is a very big requirement. It has to support at least C++ 17. Even if you do not want to write this, just write ICPX if you have the ICPX compiler, or even ICX. So yeah, this is one of the things which I was mentioning before, the optimization levels. In the case of your generic compiler optimization levels, O2 is the one which it goes by default. Okay. There are some interprocedural optimizations, vectorization, which is by default done in your code. Assuming you have inlined your code, you have followed the proper semantics of writing SYCL. O3 on the other hand, gives a bit more aggressive performance, optimizations, loop unrolling and loop blocking, but these are dependent upon your hardware. So, if your hardware supports extensive optimizations, then, extreme optimizations, then it's good. Otherwise, I would not recommend it. O2 is pretty good for any kind of SYCL, codes to get migrated. Yeah, and then the command that you use at the top is this one. Yeah, just specify whatever commands. Yeah. One of the interesting things is AOT, ahead of time compilation. So ahead of time compilation is something which is pretty, I think, how many of you know ahead of time compilation and just in time compilation? Or have heard of it in the case of, PyTorch or any of the deep learning platforms? So ahead of time is pretty good when you have your dedicated code. You want to compile it, with certain backends and certain restrictions. Okay, so there are certain restrictions of ahead of time is that you have to specify what device you are running it on, what is the end device, how it is going to be interpreted by the lower device, and so on. So to specify, for example, this is a command which specifies your SPIR64 x86 kind of backend, with AVX2. This is a CPU kind of, I would say, AOT compilation for a file called as main.cpp. Okay, so it will automatically compile in ahead of time, but you have to specify what architecture. So this minus M arg that you see over here, that is where you have to specify what architectures you are going to use. Okay. So this is just a generic flow of what commands you want to use, right? We will be coming back to and referring to these commands once we write the SYCL code. It is very important that to know what these commands do. Yeah, other optimizations are there. So I'm not going to go into those details. Typically OpenMP, vectorization, dynamic linking, level 0 runtime selections. Level 0 is something which is proprietary to Intel. We have a kind of a level 0 framework where we have lots of optimizations in case of GPU, FPGA, and so on and so forth. And we have something called as this guy, SIMD, right? I think I do not have time to cover SIMD today for SYCL, but we will show a small example down the line. Explicit SIMD, sorry, but maybe not, not here. Yeah, so just continuation of that. So this is just a command for compiling for your AVX. So this is a typical command because here you see that main.cpp is a file which does not have any SYCL kernels. So you can use the ICPX compiler without the fSYCL flag. So it is just a generic non-SYCL kernel. Okay. But this guy over here, this block reduce.cpp, right, which is a code we're coming to that, is typically having this SYCL kernels, right? So, but the last line, we want to link this non-SYCL kernel with the SYCL kernel. So, and we also provide the architecture that we want to link it. So this is the command for cross-linking SYCL and non-SYCL combined binaries. Now this is very interesting because if you have ever seen a CUDA file, right, or a CUDA source, you are going to have CUDA headers, CUDA code, as well as your non-CUDA or non-device related code, right? Let's say driver functions. Okay. Now in that case, you want to link them together before even your Python linking happens, right? So in that case, this is very important, and you can use that. Now that is for CUDA. You have to migrate it to SYCL, and then you can use this. Yeah, I mean, this is just a wrap up of what I had to say. It's probably covered. Yeah, now I move to some semantics of SYCL. Okay, now SYCL as a language, I think is very beautiful for me. But I will try to do justice to the language. There are three building blocks inside SYCL. So in SYCL, we have a component called as host and device. In deep learning, we have a concept as host and device. Your device is typically your code which gets which runs on your GPU, FPGA, or any kind of accelerator device, accelerator backend, TPUs and all. Okay. So needless to say, those architectures are different and they need faster computation. So in this case, we have the host code, right? We have an accelerator code, and then we have the host code again. This is the standard architecture. Now, in SYCL, we have something called as queue, command queues, in other words. Command queues is nothing but scheduling your buffers and your containers, data containers from your host code to your device code so that the operation happens inside the device code. Let's say if you have heard about simple operations like backpropagation in deep learning, a very complex operation. I'm saying it is simple, but it's complex operation. Jacobians are involved, derivatives are involved. So that guy happens over here inside this command queue. Okay, addition, subtraction, multiplication, division, the fundamental operations happens inside this if you want to run it in the device code. Okay, and then you have the host code where you want to just return the results from your GPU to your CPU. Let's say the most common norm. And yeah, I mean, so there are different things. One is the queue, which I talked about, pointers and buffers for holding the data, and a parallel for. This is for heterogeneous computing and scheduling the, I would say the command queues and scheduling the algorithms. So let's say if you want to have an addition, you want to put it inside a parallel for. This will execute parallelly across your devices. This is the generic code pattern inside any SYCL kernel that you write. So this is just a typical slides. So yeah, there are code samples over here, but let me move to, this is what the SYCL this is taken from Khronos. So this is what the SYCL ecosystem entirely encapsulates. So I think, we have the DPCPP compiler from Intel. We have the, the code play, adapters as well for different runtimes. We have hipSYCL as well. Yeah, and in this case, let's move to an example real quick. So yeah, just let me skim through the slides. So yeah, over here. So we talked about queues, right? Command queues. Okay. So command queues. Let's take this example over here, which is a queue, and this is how we write the queue. Queue.submit, where we pass a handler for that queue. Okay. Now this queues is it can be in order, it can be out of order in a direct acyclic graph. So the beauty of this way is that we can link and also non-link different kind of in order and out of order queues. Okay, so linear task chains are very common. And simple things should be simple to express. So that means that if auto E, right, that is the starting queue. Okay, you have another queue where we are initializing and it depends upon E. So that there is a linkage between that. Okay, by default you can schedule in order queues. It is easy to do. And let's say you have a final queue which is dependent on F. That is there is a direct linkage, 1:1 linkage over here. So this is how you write, a kind of an in-order scheduled queue, one after the other, where you schedule different, queues one after the other. Each of these queues run asynchronously. It is important to mention each of these queues run asynchronously. The operations are happening asynchronously, and there are certain conditions of, pausing where you want to perform synchronization. So let's say barrier, or you want to wait, you want to stop something. Let's say you want to synchronize all the threads on your GPU and then propagate to your CPU and so on. So yeah, let's take an example over here. Okay, so disregard this part for now. Okay, assume they are just inputs, standard inputs for your code. Just consider them as buffers, vectors, whatever. Okay, now this is the code where where we actually write how we represent and call a kernel. This is a kernel which is, let's say, a SYCL kernel, right? We are initializing a kernel. This is an activation kernel. If for those who do not know, activation is something which is a part of deep learning. I will come to that. So it is calling. You have to specify your domains. Okay, in SYCL architecture, we have something called as work groups and work items. Okay, it is similar to the blocked architecture in CUDA. 3D blocks. Okay, so the same pattern happens over here as well. We have a 3-dimensional block which kind of tries to attain different kind of contents. So let's say your grid size and the block size, it is dependent upon your memory architecture or your work group size. Okay, but this is the general pattern how you write your command queues. Yeah, so there is also a device filter inside SYCL, where we can write the device, whatever device, let's say OpenCL backend, or if you have other backends as well, let's say SYCL backend, right? You can also specify the device level as well. Now this is very interesting, is that we have the level 0 over here. So by default, in the case of our GPUs, we have the level 0 runtime as standard. Yeah, this is what I was talking about in the case of the SYCL architecture, or the memory pattern inside SYCL. So you have something called as an ND range, which is a work group or a work group kind of thing, and each of these work groups have work items. Okay, and these work items can run asynchronously, and these work groups are nothing but they contain all of the containers for your code. Okay, a subgroup is a collection of contiguous work items in the global index space. So this is what it, subgroups are represented. If you like, this is let's assume that this is a complete work group. The subgroups are like this. So let's look at another example of SYCL code where you have, subgroup copying of 1024 cross 1024 units, right? A buffer rather, across 16 work items. Okay. So you initialize your data pointer over here, right? And then after that, you submit your queue, which runs asynchronously. Here you get the global, that is the index of your data. That is the index of your work item. Okay. And for each subgroup, right, you perform any kind of computations. Over here, I'm just migrating data with modulo 16 from one buffer to other buffer, but you can do any kind of computation over here. Okay. So it can be complex computations as well. Now let's come to deep learning part, right? So reduction is one of the fundamental elements in deep learning. Reduction, as we know, that it is kind of like any kind of mathematical operation to shorten a buffer to a smaller size. So let's say addition operation, multiplication, right? So this is known as reduction in general. But there is an entire theory on reductions, but this is what it means in the case of deep learning, right? Here we have something called as a sum reduction, where we are summing the contents and we are just getting the results. I think we'll be seeing an example over here. Just give me a moment. Yeah, so this is an example over here, which shows you a corresponding code for reduction. Reduction, let's say here what we are doing here, we're trying to sum the inputs, just the diagram which I saw. So this reduction in CUDA is written over here. This is how CUDA writes, implementations, device-specific code for, reduction. Using let's say blocked diagram in a blocked architecture for summing. It can be anything. It can be sum. It can be multiply as well. It can be anything, right? So see the similar pattern that we have. We are migrating into the SYCL part. So the SYCL migration is something pretty much similar. We have reduce over group, where we are reducing over the entire work group, followed by the the SYCL plus attribute. Okay. So this is kind of like a 1:1 mapping between your CUDA code and the SYCL code. So let's look at now convolution. Okay, so convolution is another interesting operations, right? So we know in the case of machine learning and deep learning, we have convolution where for different kind of models, let's say YOLO, V5, or mobile net and all, right? This is what convolution does. Although convolution has a different theory in DSP and all, I'm not going to go into that. So over here, we use something called as cuDNN in CUDA, right? How we call the convolutions, cuDNN kernels, right? Forward kernel. Then you have which is the forward, which is actually the forward propagation of your model. Then you perform a synchronization once we get the results, and then if you want to perform any kind of backward as well. This is only for inferencing part, because you are only passing through one way. This is not a training loop, but this is just for inferencing a particular model. So here we only see a kind of forward code, and then we have a CUDA synchronize. Now let's see the SYCL kind of output over here. So for SYCL, we have a similar kind of 1DNN translation, which is by default, you can use it inside your code. So we have something called as async convolution forward, and then you can use your queues to wait, and you can just schedule a barrier for your queues so that it becomes synchronous. And then it's all just mem copies back to the host, and this is also mem copies back from host to the device. And this is just the convolution part, which is similar to cuDNN. Let's look at softmax. Now, if you know about softmax, then this is pretty much a very interesting thing. This is what softmax does, which is an activation function, which is a primal point in any kind of transformer architectures, which is the backbone of Llama or anything like that. So this is the CUDA representations, where we have the CUDA softmax forward, and typically this is where it gets used. And corresponding, we have the SYCL translation over here, which is async softmax forward, and the same pattern follows. Okay, these are all mem copies back and forth. Now let's look into the interesting part, where we come into a deep learning framework like PyTorch, right? So PyTorch is typically a deep learning framework which has 3 different components. One is graph acquisition, which is the PyTorch graph. One is graph lowering, which is lowering down to a primitive intermediate representation. And then we have the graph compilation at the backend. Now this is where it splits into different IRs depending upon your different hardware. So it can be Triton, it can be, let's say for us XPU, it can be CUDA or anything else, right? Now the kernels that we wrote, we want to add over here in Pythonic runtime and link them. So this is the way. So the SYCL kernels that we write, we link them through either CMake or through setup.py, and we patch it through the the PyTorch standard PyTorch runtime, and also beyond that as well. So how we write this, how we link this SYCL code to any kind of CMake, I'm not sure if this is visible. I might show the code. It is there in the GitHub repo in setup.py. So this is a generic way of linking any kind of device-specific code from your C++ backend to your Python backend. And typically for Intel, we use something called as Intel extension for PyTorch. which is a faster way to have and run efficient devices and runtime on your PyTorch system, on your Intel devices as well. So there is a case study on how to write transformers. So I'm going to give a brief about that. This is what the transformer architecture looks like and is the main component of all the models that you see in the internet, including ChatGPT, the one you might have been using. So here, the transformers are typically made up of this block, this guy over here, this particular guy. So it has 4 components. One is the embedding space, one is self-attention, one is layer normalization, and one is feed forward with activation, which is just the softmax which I talked about. So we are going to write some SYCL kernels. We will see some SYCL kernels probably for some of these. Let me just switch the code to the code part real quick. It's not visible. Anyways, I have the. Okay, no need. I have the codes in the slides as well, so not no issues. Yeah. So the positional encoding is kind of like generating the embedding space. We are going to have different kind of positional encoding kernels which are there. So I think the path to the kernels are also specified in the GitHub repository. So if you have SYCL with PyTorch folder, you can look it up. You are going to find all the kernels which I'm going to mention over there. So the first is the embeddings part, and the next one is the actual attention mechanism, which is the main building block of the transformers. So this is what attention looks like, and these are the blocks where we want to perform the attention. So the main concept of attention is having 3 different vectors: query, queues, and values, right? We multiply queries and queues, and then we perform a softmax regression on it, and then we multiply the result with the values. Now, in SYCL code, these are the 3 important blocks which it does this. So I abstracted parts of the code for simplicity, so that you can use this particular code. It's a standard code inside the kernels folder. So you see, you have qk dot product using SYCL. You have the compute softmax, right? And you have finally the softmax dotted with the v vector. And this is present inside every SYCL kernels actually. Every transformer code. Then you have something called as the layer normalization, which is just the code over here. Layer normalization is something to normalize the results of your layers. And how we write that in SYCL is to take the variance and then have the variance and the standard deviation, and then we try to maintain and regulate the values of those layers within that bound of the standard deviation. So this is an interesting thing because it is one of the important parts of the architecture as well. So here we have something called as block reduce sum, the code that we saw. We perform certain arithmetic operations, let's say square root and everything, and then we get the results. The next part is nonlinear activation. So this is something which is similar to the softmax kernel which I talked about. So it's pretty much the same. So you can have softmax or any other kernel for that matter. And yes, SYCL with Hugging Face is like having this kind of, if you want to use this kind of things, right, for not only for IPEX, for CUDA, you have to just specify the fSYCL target as, CUDA or PTX architecture. And the same code with transcompile for different architectures. So you do not have to write IPEX. IPEX is for Intel, but if you want to write it for CUDA, you can use the generic code which is not in ink, which is not in blue, right? You can use the black code as it is. So all the kernels that I showed over here, including this, and this, all are auto-compilable. So you can basically have the SYCL transformer implementation, which I just shared in the GitHub, right? You can use that and compile it for your CUDA backend and run it. Loop it over 24 times to get BERT. Loop it over 70 times to get, any kind of GPT-based models, let's say GPT-J, or loop it over 120 times or 300 times to get, Llama and all these kind of things, right? Which Facebook and others are doing. This is one of the leaderboards, and I think the last section is about data parallel C++, which is the auto migration tool. It is a very beautiful tool, and this is the entire pipeline, how it gets auto migrated. So you just have to specify using this DPCT, assuming you have the cyclomatic toolkit, which is there in the next slide. This is the command for generic any kind of transcompilation of your CUDA kernels to your SYCL kernels. And the SYCL kernel that you generate all the things that I mentioned till now are applicable, right? So and this is the entire architecture. And these are the steps to build your, say, you want to have the cyclomatic compile, that is the DPCT toolkit. These are the steps how to do that. So you have to clone this repo, cyclomatic Git, and then you have to build it using your compiler standards, right? Let's say you have targets x86 and NVPTX, that means NVCUDA, assuming SM90 or SM80, right? And then you perform this setVars, and yeah, once you have the values, you can get the, you can use DPCT or C2S, whatever. Right? C2S stands for CUDA to SYCL. Either you can use DPCT or C2S, and you will have all the migrated headers and CUDA files over there. SYCL files over there. Okay. So there are some default migration rules. You can also specify migration rules which are user defined. So you can specify in a YAML file which gets auto-generated. Right. For example, this is a YAML file rule 1. So for example, I want to force inline, right? So if there is a force inline attribute inside CUDA, it will get translated to inline. So this is a YAML file translation, and you have to specify that using in runtime so that you can get the correct translation. Yeah, I mean that's and if you have some time, I want to give you some performance numbers if possible. These are performance on non-DL workloads with respect to AMD, AMD SYCL and AMD hip, right? And typically, what is interesting is our numbers on GPTJ inference and performing, let's say, large language models, right? What is between Nvidia SYCL, right? What is the comparison? It is samples per second. The more samples you have per second, the greater the performance actually. Then you have your deep speed inference, right? On Llama 2. So you have deep speed kind of performance. It's pretty evident what it means over here. So outbeam means the number of tokens of a model, how it generates in the output. So for example, when you type in ChatGPT, what is my name, and your name comes out, the number of tokens, those are the number of tokens. How many tokens it gets generated is the latency. So similar performance results are there. And lastly, I think that's pretty much I had to cover. Yeah, some resources I wanted to, some resources I wanted to talk about. So repository is there, and some OneAPI samples is there. And these are some of the repositories you can take a look into if you want to perform this kind of, if you want to build your own kind of architectures, which are, let's say, transformers or anything like that. Typically, for Intel, we use PyTorch.cpp extensions. So CPP extensions under PyTorch allows you to compile any kind of device code for your hardware. So on that, we have CUDA extension, we have DPCPP extension for SYCL, CUDA extension for CUDA, right? And you can use the same SYCL file with CUDA, right? With CUDA extensions to compile for your CUDA, library, devices. And yeah, that's it. I mean, this is the conclusion that I wanted to say, and yeah, I mean, that's pretty much what I wanted to cover.
I'm not having a question, but a wish. As a wish of someone who cares about good code quality, I wish that you change your code examples, especially those that are used for people learning about SYCL, to actually use modern C++ style and less of these arbitrary constants and multiplication and stuff like things where it looks like, oh, there's a pointer with a malloc, and then what does it happen? Who owns the memory? Is that released implicitly or so? Which was confusing for me. But also the code examples look much like old style Fortran or C code, and you can do much better and simpler in C++.
Yes. Thank you for the feedback.
Yes, but I was about to say something bad.
I have two questions for you and a simple reply to what, to the claim. SYCL has two ways of accessing memory on the device. You can use the pointers, that's the Intel way, how we call it in CodePlay, and the CodePlay way is with buffers and accessors. Intel recommends using pointers because it's faster. That's it. That's as simple as that. You can build your thin wrapper file, wrapper class, on top of pointers, the raw pointers that Intel recommends, and that way you will free them when it goes out of scope. SYCL is going to work on a improved memory model, like similar to accessors and buffers, but cheaper. And I guess in the future that will be the way to go. But for now, if you want performance, this is what you have to do. And you can build your own thin wrapper class.
Yeah.
That's one thing. And then I have 2 questions for you. Can you go back to the results slide, please?
Results.
Yeah.
Okay.
The NVIDIA one, not the NVIDIA one. The comparison with NVIDIA, yeah.
Yeah. Just 1 second. Let me just, a lot of slides, so I have to skim through them. Yeah, this one?
Yeah, so
Yeah.
That was CUDA code or SYCL code compiled to PTX?
So that is SYCL code compiled to Nvidia PTX. Yeah.
Okay.
Yeah. So these are non-DL workloads. So these are deep learning. These are machine learning workloads, and some HPC workloads, but they are not deep learning, workloads. LLMs or multimodal models. No. So those models come later. Yeah.
Do you have a sense of if I wrote the same code in CUDA, what would be the comparison more or less? Would it be close?
So yeah, it would be close because we have certain internal benchmarks when we try, let's say, CUDA APIs, let's say cup thrust, CUFFT, CURAND. So we try to compile with, let's say, our own one API standards. So let's say one MKL, one DNN, and we try to have certain internal benchmarks for a healthy competition, of course. And then we try to always try to collaborate and get better results. For exascale computing and all, because our hardware actually depends. Most of the market, let's say, even from Microsoft to Meta, depends on this. On large language models and everything. So, yeah.
Okay, and just a really quick question. So you use Cyclomatic for code translation to implement?
Yes, mainly we use Cyclomatic. We are trying to upgrade it, and we are constantly revisiting our modules, one DNN, the memory samples and everything, just to make it better. Yes.
Okay, and do you have an estimate of how much time did you save by using Cyclomatic? Because I've heard that it has improved a lot in the last year.
It has. So if you get a chance, if you have one API, right, it doesn't matter what your hardware is. If you have one API installed, right, even for your CPU, right, if you have Xeon CPU, just try out DPCT, a DPCT toolkit or Cyclomatic toolkit for auto migration of your CUDA code to your SYCL code. You will be amazed at how fast it can get. It will be your copilot. If you want to write cross-compiled binaries for device-specific code, by device I mean GPUs specifically, then in this case it is a very good thing. You can definitely use it. Yeah.
Okay, thank you.
More questions? Okay, then thank you very much.
Thank you.